Dear students, in this module, we will discuss about the applications of the time-independent perturbation theory. As you remember, we studied time-independent perturbation theory in the last module. And we saw how through first-order perturbation theory, one can solve complex chemical systems. First, let us recap the time-independent perturbation theory. As you already know, perturbation theory is an approximate method that solves the Schrödinger equation of the complex system by providing successive corrections to an unperturbed problem. In this case, if we have to solve the Schrödinger equation, say H psi is equal to E psi, then in this perturbation theory, H cap, which is the Hamiltonian, is written as H0 cap plus lambda H1 cap plus lambda square H2 cap. So these are the successive corrections to an unperturbed Hamiltonian H0 cap. Similarly, the corresponding wave function psi will be equal to psi 0 plus lambda psi 1 lambda square psi 2. Here again, psi 0 is the wave function of the unperturbed system, and the rest are the successive corrections. Likewise is the case for the total energy E, which is equal to E0 plus successive corrections, which are represented through lambda E1 plus lambda square E2. All these three equations have been given in equation number 1, as you can see here. The first term in these equations 1 represents the unperturbed system, while the rest of the terms in each of the expressions of equation 1 represent the correction terms which indicate perturbation effect. Please remember that the basic assumption of the perturbation theories are that the perturbed Hamiltonian is only slightly different compared to the unperturbed Hamiltonian. And the eigenstates psi and eigenvalues E corresponding to unperturbed Hamiltonian H0 cap are known. So these are the basic assumptions of the perturbation theory. Now with all this background, whatsoever we have learned about perturbation theory and the first order perturbation effect, we will apply this theory to solve Schrödinger equation for two cases. First, we will take the case of a particle in one-dimensional box with a slanted bottom. And secondly, we will take a chemical system which will be here in this case a helium atom. Since we are studying the first order perturbation, to solve these two problems, the corresponding Hamiltonian H cap, the corresponding wave function psi, and the total energy E will be given by the set of equations 2, where as you can see H0 cap, psi 0 and E0 represent the unperturbed system, whereas lambda H1 cap, lambda psi 1 and lambda E1 represent the corresponding first order correction to the various terms. Using these equations, as we have already learned in the last module, one can very easily calculate the total energy, which comes out to be equal to E0 plus integral psi 0 star H1 cap psi 0 d tau. That gives us the total energy. Here you can see the second term on the right hand side represents the first order correction to the energy. Similarly, the corresponding wave function psi will be given by psi is equal to psi 0 plus a correction which is given by the second term on the right hand side in equation 4. Here the second term is summation m, then in the numerator we have psi m star H1 cap psi 0 d tau psi n, and in the denominator we have E0 minus Em for n is not equal to 0. So the methods for obtaining the first order correction to energy and to the wave function are very simple and can be obtained very easily using equations 3 and 4. Let's now discuss what we have already learned to two cases. First, we will take a very simple case, and that is the case of a particle in one-dimensional box with slanted bottom. The problem is very easily shown in the diagram, as you can see. Here, the length of the box is between x is equal to 0 to x is equal to L. And as you can see, on the right-hand side, the bottom is slanted. So there is a particle of mass m in this box. Now, if we have to solve this problem quantum mechanically, we will have to first take out the unperturbed part of the problem. And unperturbed part of the problem is with which you are already familiar, and you have already learnt the solution of a particle in one-dimensional box. There, as you know, the Hamiltonian h0 cap is equal to minus h square upon 8 pi square m d2 by dx2. And the correspondingly energy expression which comes is E0 equal to n square h square upon 8ml square. Here L is the length of the box and m is the mass of the particle. And the corresponding wave function psi 0 is given to be equal to 2 by L under root sine n pi x upon L. These solutions are the solutions with which you are very well familiar. But please remember, these solutions were obtained for a particle in one-dimensional box of length L. There was no slanted bottom there. Now in our problem, the bottom is slanted 1, and therefore we will see how this introduces a perturbation and then how we solve it. As we have already learned in equation 2 earlier, the perturbed Hamiltonian for a particle in one-dimensional box with slanted bottom will be given by h1 cap equals kx upon L. This is our first order perturbation to Hamiltonian. Now, once we know the perturbed Hamiltonian, this first order correction to the Hamiltonian, using equation 6, which we have already seen, which gives us the first order correction to the energy due to perturbation, one can find that E1 is equal to psi 0 star h1 cap psi 0 d tau. Now in this equation, if we put for h1 cap equals kx upon L and then put the values of psi 0 star, which is 2 by L under root sine n pi x upon L, because it is psi 0 star and psi 0, it gets squared, and ultimately on the solution of this integral between the limits 0 to L, we get the corresponding answer, which is equal to k by 2. So k by 2 is the corresponding correction to the total energy. Unperturbed energy was, as we had already seen, n square h square upon 8ml square, and k by 2, which we get now, that will be the correction to that energy. So once we have this first order correction to the energy, then the total energy of the particle in a one-dimensional box with slanted bottom is given by E is equal to n square h square upon 8ml square plus k by 2. Similarly, one can also calculate the first order correction to the wave function also, because although that may not be very easy to solve, but we have already seen the expression for calculating the first order correction to the wave function. After having studied the application of time-independent perturbation theory in the form of first order perturbation to the problem of particle in one-dimensional box with slanted bottom, let's take up how this time-independent perturbation theory can be applied to a chemical system. And the simplest chemical system to study is the helium atom. So now we will study this application to the problem of helium atom. Now, if you look at helium atom, it is a three-body system because it contains one nucleus and two electrons. And the first thing to solve the problem of helium atom is to write the Schrödinger equation for helium atom. And for writing the Schrödinger equation for the helium atom, we need to write the Hamiltonian for the helium atom. As you can see from the diagram here, that the helium atom has two electrons and their coordinates are R1 and R2. And the nucleus has a charge of +2. Now the Schrödinger equation for helium atom, that means the Hamiltonian, can be written as H cap is equal to minus H square upon 8 pi square ME. ME is the mass of electron. Then in the parentheses we have Laplacian operators for electron 1 plus Laplacian operator square for electron 2 minus H square upon 8 pi square Mn Laplacian operator n square. That means this term represents the kinetic energy part for the nucleus, whereas the first two terms represented the kinetic energy part for two electrons, 1 and 2. And then the next term is minus 2e square upon 4 pi epsilon 0 r1. This is the attraction between the nucleus and electron 1. And why it is negative? It is negative because attraction terms are negative, whereas repulsion terms are positive. Then the next term is minus 2e square upon 4 pi epsilon 0 r2. This is the attraction term between nucleus and electron 2. And lastly, you see the interelectronic repulsion term. This is positive because this represents the repulsion between two electrons 1 and 2, and therefore R12 in this. You see this term is E square upon 4 pi epsilon 0 R12, where R12, as you can see from the diagram also, is the distance between the two electrons 1 and 2. Please note that in this Hamiltonian, Me represents mass of electron and Mn represents the mass of the nucleus. Del squared El represents the Laplacian operator for the electron, and del square N is the Laplacian operator with respect to the coordinates of the nucleus. Now this Hamiltonian, which we just discussed, it can be further simplified by an assumption that since the nucleus is much more massive than the electron, therefore in this case nucleus can be considered to be almost at rest, and therefore its kinetic energy contribution can be ignored. And therefore the Hamiltonian with this assumption becomes correspondingly H cap equals minus H square upon 8 pi square Me del square electron 1 plus del square for electron 2. And then minus the rest of the three terms, as you can see, they represent, the first term is the attraction term of the nucleus with electron bonds, second is attraction term of the nucleus with electron 2, and the third term is interelectronic repulsion. One thing more which is very important to note in this Hamiltonian given in equation 10 is that the last term, which is the interelectronic repulsion term, is the term which we have already discussed, which makes the solution of the Schrödinger equation almost impossible. And therefore, if One way can be that we can neglect these terms and therefore rest of the problem becomes exactly solvable. If we neglect this term, then the whole problem reduces to the corresponding Hamiltonian, which becomes equal to minus h square upon 8 pi square me del square electron 1 plus del square electron 2 minus 1 upon 4 pi epsilon 0 2e square upon r1 minus 2e square upon r2. So this is the corresponding Hamiltonian when the interelectronic repulsion term is neglected. And therefore, this becomes the corresponding Hamiltonian of an unperturbed system in our present case. As you can very easily see, equation 11 can be rearranged to give the corresponding Hamiltonian equal to minus h square 8 pi square me del square electron 1 minus 2e square upon 4 pi epsilon 0 r1. This all taken together. These first two terms therefore represent electron 1, and second term, third and fourth, minus h square upon 8 pi square me del squared electron 2 minus 2e square upon 4 pi epsilon r square. This represents the corresponding case of electron 2 attached to the nucleus. So this is how we can rearrange this Hamiltonian. If one looks carefully at equation 12, one can very easily see that when we made the assumption of the nucleus being at origin, and when we neglect interelectronic repulsion term, the Hamiltonian of the helium atom gets converted into the sum of two hydrogen-like Hamiltonians, or one electron Hamiltonian. Or one can say that the ground state Hamiltonian of helium atom is a sum of two helium ion terms. That means one electron Hamiltonian. This is a very important interpretation of this Hamiltonian. The zero order ground state wave function for helium atom is taken now as a product of individual electron wave functions. That means the wave functions of two helium ions not interacting with each other. That means they are being approximated as hydrogen-like one electron wave functions. So the ground state unperturbed wave function for such a system will be psi 0 in parentheses we have r1 comma r2 equals psi 1 r1, and then product next term is psi 2 r2, where one electron hydrogen-like wave functions which you have already studied are given by, you can see in equation 14 is given the one electron hydrogen-like wave functions in the ground state, and this is equal to psi is equal to 1 upon under root pi z upon a0 raised to the power 3 by 2, and then multiplied by e to the power minus zr upon a0, where a0 represents the Bohr radius and z is the charge on the nucleus. In the case of helium atom, z will become 2. And therefore, one can very easily say that the ground state helium atom energy for this unperturbed system will be given by E0 is equal to minus 2 pi square me z square E4 upon n square h square 4 pi epsilon 0 whole square minus 2 pi square me z square E4 upon n square h square 4 pi epsilon 0 whole square. So it's basically the same term coming 2 times. Here you can see the table 1. Table 1 gives you in a nutshell the comparison between the energy of hydrogen atom, the energy of the helium atom, when it is considered as an unperturbed system where we neglect interelectronic repulsion and also the energy of helium ion. If you see at the left hand side, energy of the hydrogen atom is given by the expression EH is equal to minus 2 pi square me z square E4 divided by n square h square 4 pi epsilon 0 whole square. Here, please remember we are talking about hydrogen atom and therefore Z will be equal to 1 and therefore Z square also is 1. But if you look at the correspondingly right hand side, energy of the helium atom, as I said it already and we have already learned that in an unperturbed system where we neglect interelectronic repulsion, energy of helium atom can be taken to be the sum total of the energy of two helium ions. So the first term in the energy of helium atom is minus 2 pi square me z square E4 upon n square h square 4 pi epsilon 0 square. Minus second term is also similar to the first term. But if you look at the corresponding term on the left hand side in EH, that is also the similar term. But the difference will come that there Z was 1 because it was hydrogen atom. Here it is Z will be 2 and therefore Z square will become 4. And both the terms in the energy of helium atom, the first and the second, they represent the energy of the corresponding helium ion, which is given by the expression minus 2 pi square me z square e4 upon n square h square 4 pi epsilon 0 whole square. The only difference you can very well now understand is that hydrogen atom and helium ion are similar in the sense that both are one electron systems. Only thing is that in hydrogen atom, the nuclear charge Z is 1, whereas in helium ion, the nuclear charge is 2. One thing more which is very striking and which is important to see from this table is, and if you look at the left hand side bottom, you see that the energy EH has been given in the corresponding atomic units. And on the right hand side, the same energy is being given for the helium atom in atomic units. You have already learned the concept of atomic units and you know it very well that in atomic units, things simplify, mass of the electron is taken to be unity, charge is also taken to be unity. So the only terms which are basically left would be the corresponding terms which are coming here. So it's just the application of atomic units to these expressions and they look very simple and easy to remember. Now you can have a look at equation 16, which is very simple. As we have already discussed that the energy, ground state energy of the unperturbed helium atom will be equal to 2 times the corresponding energy of helium ion. And as we also saw that the energy of helium ion is changing because of Z. So this becomes equal to 2Z square EH. And since Z is 2 in the case of helium atom, so the total energy becomes 8 times the corresponding energy of hydrogen atom. That means the ground state energy of helium ion unperturbed system. Please remember here unperturbed system means the system where we have neglected interelectronic repulsion. And that energy is equal to 8 times the corresponding energy of hydrogen atom. So you now have seen that we have been able to solve the problem of helium atom neglecting the interelectronic repulsion term. But we have to take into account this interelectronic repulsion term in the form of a perturbation. And this interelectronic repulsion term represents the perturbed Hamiltonian. As you can see, H1 cap, which is given in equation 17, is equal to E square upon 4 pi epsilon 0 R12. Now this is basically the Hamiltonian using the normal units. If we use the corresponding atomic units about which we talked earlier, this Hamiltonian becomes much more simpler, and even the ground state wave function of the unperturbed system also becomes very simple, and these are given in equations 18, 19 and 20. And ultimately you can see that the perturbed Hamiltonian, if we take it in atomic units, this just becomes 1 upon R12. This is because of the fact that electronic charge in atomic units is taken to be unity. Now with this perturbed Hamiltonian, we can apply the first order perturbation theory to calculate the first order correction to the energy for the case of helium atom. As you already are familiar with, the first order correction to the energy is given by the expression E1 is equal to integral psi 0 star H1 cap psi 0 d tau. This is the expression which we have used already many times. Now in this equation, if we put the details value of psi 0 star, then H1 cap, etc., and then we integrate it, as you can see, we are doing it to equation 22. We get the corresponding value of the E1, which is the first order correction to the energy, to be equal to 5 by 8 energy of helium ion. This is very important. So we are now able to calculate the first order correction to the energy. Earlier we had calculated the ground state energy of the unperturbed helium atom, and that was when we neglected the interelectronic repulsion term. After having calculated the first order correction to the energy, now we are in a position to calculate the total energy of the helium atom taking into account the perturbation term. And this total energy of the helium atom, as you can see, is given in 24, which on further simplification in equation number 25, we get energy of helium atom is equal to 2 times the energy of helium ion minus 5 by 8 times energy of helium ion. This becomes equal to 11 by 8 energy of helium ion. And since energy of helium ion is equal to 4 times the energy of hydrogen atom, this on further simplification gives us 11 by 2 energy of hydrogen atom. If we look at this expression which we just discussed, if we want to calculate the ground state energy, that means for n is equal to 1, then energy of hydrogen atom in atomic units is half. And if we put it and calculate the corresponding energy of helium atom, this becomes 11 by 2 minus 11 by 2 into energy of hydrogen atom, which is half, and therefore this becomes minus 2.75 atomic units. And that is the energy of helium atom in ground state calculated using first order perturbation theory. If this value of energy, which is 2.75 atomic unit, is compared with the corresponding experimental value of the ground state energy of the helium atom, which is 2.9033 atomic units, one can very easily see that there is an about 5% error. The results indicate that the perturbation theory gives fairly good results for complex quantum systems. What we have calculated just now is the energy of the helium atom, the total energy in the ground state, which is 2.75 atomic units. This we have already learned. Sometimes you will be finding in literature the energy value being reported in electron volts. That one can very easily do, because one atomic unit is equal to 27.21 electron volt. So if we multiply 2.75 atomic units with 27.21 electron volt, then in electron volt, the ground state energy of the helium atom will come out to be 74.83 electron volt, of course with a negative sign. So in this module today you have seen the successful application of time-independent perturbation theory to two problems. One was the problem of a particle in one-dimensional box with slanted bottom. Now, for this system, it would not have been possible to get exact solution easily. Therefore, in this problem, we applied first-order perturbation theory and found out the solution. And we can also find out not only the first-order correction to the energy, but also the first-order correction to the wave function. Second problem which we studied was the problem of helium atom. This problem was difficult to solve or impossible to solve because of the interelectronic repulsion term. Here also we applied time-independent perturbation theory and split the Hamiltonian into two parts. One was the Hamiltonian of the unperturbed part, and then there was a first-order perturbed Hamiltonian, which was the interelectronic repulsion term. So using all these, what we have already learned, the theory part, we could calculate the total energy of helium atom. And you have seen that in the case of helium atom, the energy which we calculate using time-independent perturbation theory comes very close to experimental value. The error is about 5%, which is quite reasonable. And therefore, that shows that perturbation method is a fairly successful method, a successful approximate method to solve the Schrödinger equation of complex systems. We have taken one chemical system and we have taken another system which is not chemical, but there also we could solve it. So herein lies the strength and beauty of the perturbation method. So now you have seen, and now to summarize all the details, you have seen that perturbation theory is an approximate method that solves the Schrödinger equation of the complex system by providing successive corrections to an unperturbed problem. We have seen that the time-independent, non-degenerate first-order correction to Hamiltonian, to the energy, and to the corresponding wave function are given by the various equations which we have already seen. Using these equations, we found that the first-order correction to the energy for helium atom is given by E1 equals minus 5 by 8 energy of helium ion, and which on further simplification becomes 5 by 8 Z. And we have also seen that the first order perturbation theory on helium atom results in the energy equals to minus 74.83 electron volt, or if we represent it in atomic units, minus 2.75 atomic units, which is fairly comparable to the experimental value of minus 79 electron volt or minus 2.903 atomic units. And this calculated energy is within 5% of the experimental value.